Oh, you want to sit here or? Let's go on the side, otherwise I can't see.
I'd like to begin in the way that we do by expressing my respect to the traditional owners of this land, Gadigal people, the traditional custodians of the land. I pay my respects to them, to elders past and present. It's my very great pleasure to welcome you to UNSW and to this public lecture by Professor Lynne Billard, a lecture on the role of mathematics and statistics in science and society. Lynne was born in Australia. She was born in Toowoomba in Queensland, and she is an alumnus from this university. She graduated from UNSW with first-class honours in statistics in 1966, and then she became one, if not the first, one of the first female PhD students in mathematics and statistics, with her degree awarded in 1969. Lynne credits her mother's intelligence and a cadetship at the University of New South Wales as two of the forces that helped her through what has been a remarkable career. She's had periods of employment at the University of New South Wales, Australia, the University of Birmingham in the UK, State University of New York, USA, University of Waterloo, Canada, and then she remained in the USA, continuing with appointments at Stanford University, Florida State University, the University of California, Berkeley, and the University of Georgia, where Lynne is currently. Lynne attributes this career path in part to an interest in travel, but of course it has to be attributed a far greater part to academic excellence, and that has in turn, I think, facilitated this interest in travel. Professor Billard is currently a professor of statistics at the University of Georgia. She's one of the world's leading statisticians. She's internationally renowned for her research that spans many different areas: stochastic processes, sequential analysis, statistical inference, time series analysis, and symbolic data analysis. She's an author and editor of numerous books and journal articles, and she has served as president of the two largest statistical societies in the world, the American Statistical Association and the International Biometric Society. She's a recipient of numerous honours, including in 2011 the Janet L. Norwood Award for Outstanding Achievement by a Woman in Statistical Sciences, and in 2013 the Florence Nightingale David Award by the Committee of Presidents of Statistical Societies for exemplary contributions to education, science, and public service. Professor Billard's visit to UNSW has been sponsored by the Girls Do the Mathematics program that was established by three of our female academics, Adele Foster, Catherine Greenhill, and Inga Coe, more than 10 years ago. This program is well aligned with the UNSW strategy to improve the representation of females in science, technology, engineering, and mathematics. And as part of this program, we're very pleased to honour Professor Billard with another award. And this is the inaugural UNSW Women in Mathematics and Statistics Ambassador Award. And we have with us here today Vice Chancellor Ian Jacobs, who will present this award today.
Thank you, Bruce. It's great to be here. As you, I hope, all know, in our strategy, which I was just discussing with Professor Billard, equality and diversity is a really important theme. And ensuring that women students and women staff have equal opportunity with men is a key step. And I think that the Women Do Maths scheme is a great help in achieving that objective. Professor Billard, you are a wonderful example of what can be achieved if you're given the right opportunity at the right time. You were just explaining to me, I think, that you did get a scholarship, cadetship to come from Queensland to this university, and that's how your career started. So whoever set up that cadetship scheme has our thanks. Your career is an extraordinary career, and we're very proud that you're a UNSW alumnus and that you stand up for the university, and that you are the first recipient of the Women in Mathematics and Statistics Ambassador Award in 2016. Congratulations, Lynne. That round of applause just gives you an indication of how much you're valued. My loss is that I've got to go to another event now. So I will miss hearing live your talk, but I understand it is being recorded, so I will take an opportunity to see it later. Thank you very much for being here.
Thank you.
Excuse me.
Thank you.
Thank you.
So it's my pleasure now to introduce Lynne to you all, but to let Lynne now give her talk on the role of mathematics and statistics in science and society.
Well, thank you. I did not expect this. I didn't even know I was the first person on this. But as Professor Jacobs said, that cadetship that I got, the mathematics cadetship to come here, and my mother, both of them were really powerful influences on my career, and I can't thank either of them enough for that. Anyway, I'm very happy to be here, and I do see a lot of mathematicians. I thought that most of us would be non-mathematicians, so I have prepared a talk to basically to the non-mathematicians to let them see that mathematics and statistics really is important in society. And I plan to work through some vignettes fairly slowly because I want you by the end of the talk to be able to do those things yourself. So a long time ago, Wells said statistical thinking will one day be as necessary for efficient citizenship as the ability to read and write. And of course I think that that's the present and also the future. So suppose someone told you that some particular action, for example drinking coffee, will increase your risk of cancer threefold, in other words 300%. Are you concerned? Now this actually was an article in the newspaper a number of years ago, and I knew the people that did that study. And I asked them, I said, well, what's it increased from? 10% to 30%? I might be concerned if the increase is 10 to 30%, but if it goes from 0.0001% to 0.003%, I don't care. I'm going to have my coffee. Okay. And so the conclusions, the point here is that conclusions have to be in the context put into context. So coming back to the question, what do we mean by mathematical and statistical thinking? And so as I started to say before, I'm going to look at 4 or 5 vignettes and work our way through them very carefully and see what we can decide. So these are places where mathematics and statistics have been used, not necessarily correctly. There's some seats down here if you want to come down here. All right, so a couple of questions. An opinion poll asks the question, is the internet connected to your house, yes or no? Will you vote for the coalition or the Labour candidate? Do you prefer hamburgers or cheeseburgers? And so on. In each of these cases, there's a choice. And the aim is to estimate the proportion of the population supporting one particular choice, one particular outcome. And so the question I ask is how many people are polled, have to be polled in order to be 95% confident that the estimate that they get is within plus or minus 3 percentage points of the true value. Statisticians in here know that this is the formula. The number polled is approximately, in this case, 1068. So the 1.96 relates to this 95%. You change that, and you change the 1.96. You change the 3%, you change this here. And so the question I ask you, are you surprised that it's only 1,068 people that have to be polled? And you go home tonight and look at the national news, or tomorrow night, and there'll be an opinion poll on the television. And if you look at the small print, or at least there's one every night in the US news, and you look at the small print at the bottom, and it says accuracy plus or minus 3%. You've seen it? And you can sit there to your mate and say, ha-ha, I know how many people they polled to get that answer, 1,000, and they'll be suitably impressed. They may just think you're, well, anyhow. But statistics can do that, and you can get a pretty accurate answer, all right? And of course, you've got all sorts of assumptions that I'm not going to go into. All right, so now I want to look at a particular question. You want to estimate the size of a species, bird population, say, think birds if you like, and try to imagine going out into the forest counting the birds. They won't keep still long enough for you. But the idea is you capture 200 birds and you add a marker on them, and then you release them. And then you come back later and you capture 100 birds. And 80 of those had a marker and 20 did not. And you want to estimate the population of birds. And this is enough information to do that. So let's rewrite those first two lines this way. So we've got the first catch. There's 200 of them. They're all marked. All right. We've got the second catch. 80 of these 200 are in the second catch because they were marked. Right? With me on this? And fill in a bit more. What we want to find, of course, is this total population in. Fill in a bit more. So of the second catch, 80 of them were marked, which means 20 were not in the first catch. They are unmarked, so they're not in the first catch. All right, there's a total of 100. Likewise here, we had 200 in the first catch, 80 of them were in the second catch marked, and so therefore 120 were not in the second catch. Okay, not marked. And we want to estimate n. So what might that be? Think about it intuitively. Well, I'm going to suggest that 80 here marked is 80% of 100. So therefore, 200 must be 80% of n. Yes? And yes? And that's 250. And notice that 250 is just 200 multiplied by 100 divided by 80. Okay? That's always the case. Mathematics is elegant. It's simple, it's elegant. It's beautiful. Okay? And you've also got these birds here that weren't caught in any time, either of the two times, but you can estimate that because you've got all of these numbers, so you can work out what that is. And so the rest of the little table is that. And in particular, you had 30 birds that weren't caught either time, but you can count how many were totally missed. Okay? And for those of us who are mathematicians, this is nice, elegant. For those of us who are not mathematicians, we think this is magic, but it's not magic, it's just beautiful mathematics. Okay, so another application of this is in the census. The first catch corresponds to, you send in your census forms. And if you've ever been involved with the census process, not everyone sends in their forms. Okay, not all the birds are caught on the first catch. And so then you come back, you go around knocking on the doors, and you have a second catch, a second count sample, and 80 of them were marked. 80 people had actually turned in their census form, so you can measure the number who completely missed in the census, and so you can get a number for the entire population. So that's a simple way of how a census works in that way. Nice, easy, yes? All right, that's mathematics for you. All right, now I want to do another vignette. I have these data. We have these data. And so each dot here represents a point in, you've got Y down here is the growth of this lactobacillus, something I can't pronounce, and X is the amount of vitamin B12, right? And so you've got a bunch of these pairs of observations, and you want to ask the question, is there a relationship between the growth, between the Y, and the dosage, the amount of vitamin B12? And So, yes, we want to fit a line through here, but if that's a line, but it's not very good, is it? And that's another line, and that's not very good either. Okay, there are in fact an infinite number of possible lines to go through those data. And there's two more. Now it's getting harder to see visually whether those fit well or not. Are they good or are they not? So now we've got a little bit of elementary statistics. How do we decide on which line is the best line? And so what we do is we just take the difference between the little black dots is what you observe. Let's take the red line. That's what the expected value would be under best line. You take that, you've got this. Don't worry if you're a mathematician, a non-mathematician, don't worry about this, but there's an equation there. And it's a little bit of calculus to find estimates for these, the majors. And if we do that for these data to fit a linear relationship, that's the equation. Okay? Looks pretty good. Okay? And so this 0.627 is the value on the intercept, the y-axis. The 0.077 is the slope of this line, if you want to get technical. Okay? But maybe you want to fit a quadratic equation, and that fits even better. I'm not going into details, and there's a comparison of the two. All right? And then, so there's always many types of equations. You can fit this sort of model or this sort of model. And in fact, for these data, if we transform the data, we can get a better fit. And so we've got that if we do, and this is not the traditional log, I've forgotten the log, but it's a very complicated log, you know, like base 8.5 or something, function, and it's a beautiful thing, okay? So, mathematics is beautiful, statistics is great, you can do this, all right? Okay, so let's come back to the original data. I want to look at another aspect of this. Look at this observation here. Okay? What about, is it just an outlier, as I suggest here? All right? Or is it a typo? Did we put in -5 instead of +5, and here it is, and if it's down here, it clearly belongs to the data set. All right? You all see that? What about this observation? It's not so obvious. This one is very obvious. It's a typo. This one, not so obvious. Okay? And that gets us into outlier, influence functions, models, and very large data sets. Because this particular data set, it's old. It's 1951, and it's small. Old data sets are small because you couldn't handle large data sets. But for those of you who are 20, and maybe those of you who are 40 as well, the challenge is to develop computer methods so that instead of eyeballing it, you can computer eye it, okay? To develop methods because you've got large data sets, you've got many dimensions. This is just 2 dimensions. You've got many dimensions, many observations. How can we eyeball it? How can we get in there to identify whether or not an observation is a typo, whether it's a true outlier or what? Okay? So that's a challenge for those of you who are so inclined to work on that. Another data set is this. So here we've got a bunch of zeros and we've got a bunch of numbers here. And the question is, what do we do with those zeros? Now, when these data were originally analyzed, the people doing the analysis ignored the zeros. And this is what happened. Some of you remember this. ignoring observations can be costly. Okay? So when you're eyeballing those data, or when you develop your programs, you're going to make sure you're handling it properly. Okay? You can't just ignore observations. Okay, that outlier that was a typo, that's different. Okay? But this is not. All right? So let's go back to those data. I've got the zeros in red now. Okay? The blues, and what this is that the y variable here is the number of O-ring failures. Okay? And the x variable across here is the temperature. And so, you know, different shuttle excursions, I suppose. Okay, some of them had 2 O-ring failures and some of them had 0, but 0 is not nothing. Okay? Nothing, there's nothing here at 40-degree temperature. These are Fahrenheit temperatures. There's nothing here. But 0 is not nothing. 0 is a value. Okay? And so you can't ignore them. All right? This purple line is the temperature the morning. It's 32 degrees. It was the temperature the morning that the Space Shuttle Challenger lifted off. Had these data been analyzed correctly, that's the fit. And depending on the model, you had 4 to 6 failures of the O-rings, and the maximum number was 6. Had they analyzed those data correctly, that shuttle would never have lifted off. As I said, ignoring observations can be costly. Statistics is wonderful. It can do this analysis, but you better make sure you do it properly. Okay? You can't just throw away observations. Is that okay? You understand the difference? Very sadly, yes. All right, so now I want to look at something. Oh, no, I forgot this one. All right, I do a lot of work with poultry scientists, so I had to show you this. So this is the x variable is the age in weeks, and the y variable in this case is egg production. All right, and so it increases and then it drops off. It could also, if you did, you know, they fatten up chickens to sell for us to eat, and you know, it gains weight and then it drops off. And if you change weeks to years, it could be us. Our height increases and it drops off as we get older. There are tons and tons of growth models that look just like this. Change the story, but you get this. And again, it's just fitting a regression of some form of model. It's not the simple linear regression that we had initially on the earlier example, but that happens a lot. Statistics is powerful. All right, so now I want to look at another example, and that is there a relationship between smoking and lung cancer incidence? Think about it. All right. Got these data. These are real data. And the thing is, for each individual, they had what? 2,714 individuals. The daily average number of cigarettes smoked, here they are. Did they have lung cancer? Yes or no? So there were 55 people who smoked 1 to 4 cigarettes and had lung cancer. All right? And bear in mind this question, is smoking and lung cancer related? So if you collapse, I'm just going to collapse this table into a smaller one for our purposes here. So I'm saying those who didn't smoke at all or smoked 1 to 4, that they were non-smokers. All right, so they had 7 plus 55 is 6, there were 62 of them. All right, and then these categories, I'm calling them smokers, and those add up to 1295. Is that right? You see what I've done? And likewise for those who didn't have cancer, collapsed it. Does So the question is there a relationship between smoking and lung cancer? So I'm going to, run out of space on this page, so I'm going to repeat bits of this. There's our collapse table. And so I want us to think about bits of this. Let's see. The proportion of non-smokers. The proportion is 252 over 2714. Is that okay? You all agree? It's equivalent to saying that's the estimated probability of non-smokers. Likewise for smokers. 2462 over 2714. Yes, so that's the probability of someone being a smoker. Okay? Alright, so now I want to look at the same sort of thing, but for cancer, yes or no. The proportion who did not have lung cancer is 1357 divided by the total number, 2714. Is that alright? It's the probability that you didn't have cancer. Likewise, the proportion that you did have cancer, so the total number of cancers, 1357 divided by 2714, so that's the probability that you did have cancer. Okay? So, we're looking, is this relationship? Is there a relationship? If smoking and cancer are independent, all right? If these are independent, then, okay, a little bit of statistics here. The probability of being a non-smoker and not having cancer is the product of these two probabilities. So the probability of a non-smoker is 252 over 2714. All right? The probability of no cancer, where are we? 1357 over 2714. All right? So it's the product. All right? So that's the probability of being a non-smoker without cancer. So of all the people, 2714, how many might we have who, the total number of non-smokers without cancer, and so we take this probability and multiply it by 2714. Does that make logical sense? Even if you're not a mathematician? I hope, because that's what it is. All right? So again, I'm going to go over the page and run out of space. I'm going to repeat some of this. That's the bottom. If the smoking and cancer are independent, we've got the total number of non-smokers who don't have cancer is this. This 2714 cancels with this one. Okay? So we can write this as the expected number of people who are non-smokers without cancer. So here we go, and it's 126. You can do the arithmetic tonight. All right? Now notice again, 126. It's this 252 multiplied by this divided by this. Mathematics is elegant. It's beautiful. Okay? Simple. All right? So you get that. And you can fill in these other gaps exactly the same way. All right? This one here is the product of 2462 multiplied by 1357 divided by 2714, and the arithmetic, this is what it is. Okay, so the question is there an association between smoking and lung cancer? So what we want to do is to compare what we observed with what we would expect under the assumption that smoking and cancer are independent. Okay, so these were values calculated under this assumption, if they're independent, if there's no association there. Okay? So we want to compare this with this and so on. All right? So I'm not going to go into the details of that. Well, maybe I can. So you're going to 62 minus 126 squared divided by 126, and then you do it for each cell, okay? And you calculate a value, which in this case, well, you do it over all 4 cells, and you get Q statistics 71.7. And then I'm really going to skip the statistical theory behind it, but this has a distribution. You compare it with table values, and in this particular case, if this Q value is greater than 6.6, then you'd say there is, oops, I went too fast, an association, all right? 71.7 is clearly much greater than 6.6, okay? So yes, there's a relationship between smoking and lung cancer, okay, based on that analysis. But what's our conclusion? Do we conclude that cancer causes smoking? Why not? Or do we conclude that smoking causes cancer? I see some nods, but we don't have information here to tell us that. Okay? All the statistical analysis can do is tell you there's an association. Okay? So the 2 original authors, Dahl and, I've got the name already, but anyway, it's a famous data set. Hill and Dahl, yeah. One of them was a medical guy, so this helps direct the medical research. Yes, there's an association, so then they know how to, do whatever to find out, does cancer cause smoking or does smoking cause cancer? Okay? Statistics is powerful, but all we can say is that there's an association, not, as I've got up here, association or causation. We can't say what causes what. So this is one of the big mistakes that we see in the newspaper. Someone does a study and they say, oh, cancer causes smoking or something, okay? When in actual fact, all they've found is an association, but they've given an interpretation to generate a headline. All right, and tied in with this is something called Spurious Association. And this is where you've got 2 things. Murders, the number of murders and the number of people in church going to church, and they're both increasing, but they're increasing because the population is increasing, not because one is causes the other, okay? Stork spring children. I actually had that data. There's actually a data set showing stork spring children. It's a Danish data set. I couldn't find it to show you. It's just the time of the year that children don't get, they're not born uniformly across the calendar, across the year. And there are certain times, and it coincided with the times that storks arrive in Norway, in Denmark, I'm sorry. So, here's another one about spurious. I don't know whether you can read that. I'm not going to read it all, but I'll read a few lines. Evils of pickling. So, pickles are associated with all the major diseases of the body. Eating them breeds war and communism. They can be related to most airline tragedies. Auto accidents are caused by pickles. There exists a positive relationship between crime waves and consumption of pickles. For example, nearly all sick people have eaten pickles. The effects are obviously cumulative. 100% of all soldiers have eaten pickles. Which one am I going to go to next? Of the people who were born in 1839 who later dined on pickles, there's been 100% mortality. Be careful about those pickles, all right? All pickle eaters born between 1849 and 1859, I should change those years. I mean, this is someone's famous page that I've copy. All people, pickle eaters born during that period had wrinkled skin, lost most of their teeth, had brittle bones, and failing eyesight if the ills of pickle eating hadn't already caused their death. And it goes on. Okay, so it's an example of you know, spurious correlation. Think of the stork and the children, if you like, well, it's the evils of pickling. So it's all good fun, but you know, what's really going on is that so often, those of us who are trained statisticians, we grind our teeth and we hang our head because we see these wrong associations being interpreted as causation instead of association with spurious association. Okay, so I started out with Wells, looking at, he was in the 1800s, and he said statistical thinking will one day be as important as reading and writing, and I totally agree with that. I actually think it's mathematical thinking as well as statistical thinking. I don't make a distinction there. I think of mathematics, statistics as the tool. It's the racket that you have in your hand when you go out for a game of tennis. And you look a little silly running around the court without the racket. Tennis could be engineering or whatever it is you're doing in science, but it's our tool, it's the tool. Wells was the 1800s. Now I want to jump. This is something that one of my students, he graduated less than a week ago, all right? And he just did this. And again, deliberately, where's Robert? He's going to object that I don't have a y-axis or an x-axis, so I've deliberately left those off. You can put what you like. You can put the vitamin D, vitamin B12 that we had earlier, and the growth of the whatever it was that was growing. You can have years across here if you're from economics, and this might be gross national product. This could be the amount of protein in the feeds if you're fattening up chickens or cattle, and this is the weight gain or what have you. Okay, but you put your own story on that. But notice that the data are not dots, not points. They're rectangles there, and that's because when you get into these massively large data sets, okay, the computers can't handle even the regression thing. We've got to invert a matrix. The computers usually can't handle that. They can save the data set, but you need more space to do the analysis. You need more computer space. So, and it may be that you're not interested in individuals. You may be interested in categories of individuals. And so you aggregate the data, and so in this particular example here, for the x's, each variable, it's instead of a point, it's an interval, here to here, and likewise for the y variable, it's an interval, okay? And if you've never seen these sorts of data before, I promise you, you're going to see them a lot in the future, okay? This is part of the future. It's not the only way to handle very large data sets, but it's a very important way to handle very large data sets. And so you've got those data, and the question is, are there groupings? You want to cluster them into natural groupings. I don't know whether you can see any groupings there. Of course there are, I wouldn't be showing it to you, but there they are, and if I put them into colors, you can sort of see them a little better, all right? There's 3 clusters here, but these clusters were formed by using regression to inform the clustering. So what happened is you divided the data up into 3 groups because you wanted 3 clusters. You fitted a regression line through each cluster, and then you had distance measures from each observation, each rectangle to a regression line. And then you shifted the observations around, moving it to the closest regression line, and then you redid it's an iterative process, you redo the regression, reshift, and you finish up with a cluster, with the 3 clusters. And Now I think those clusters are pretty obvious, at least they are to me. And another example is this one. You look at those data, it's even less obviously clustered than the previous example, but once you've done the analysis, there are clearly two distinct clusters there. And again, it's a regression analysis that informs the cluster. So that's what we're going to see a lot of in the future, these big data, be it intervals in this case. I think it's important. I hope you do too. But for those of us who are mathematicians, mathematical thinking here is crucial. Okay, you've got the logic, you have to write a lot of computer programs, but you've got to be awfully logical. You need the mathematical statistical skills thinking behind you in order to achieve this. And that's what I had to say. So for those of you who don't recognize those photos, the one on the left was the upper campus when I arrived in the 60s. And someone's playing football, and this is the, you know where this is. It's a very different place today than it was in the 60s. But it was a beautiful campus. So, anyone have questions?
Thank you.
Sorry.
Wonderful call. She's happy to answer questions.
What do you define as causing something?
Well, smoking can cause cancer, but cancer doesn't cause smoking.
But the Baldwin Hill study only showed association, it didn't show causation.
That's right, and that was the point. You've got the statistical analysis that showed association. Then the medical people go off and try to work out. They do more experiments, more studies to work out, is it this or is it that? Okay. All we can do as statisticians is inform, in this case the medical person, or inform the scientist about what's going on.
I'm sort of piggybacking on that question, but then surely the medicos use statistics to infer causation.
I'm sure they do, but not that way.
Yeah.
I can't. The medical people are actually pretty good at using statistical analysis. Sue, you can probably answer that better.
Well, I don't know how they would have done it, but these days they use a laboratory animal. And that, in other words, you set up an experiment, and it's through the design of the experiment and that you can show causation, plus the development of the understanding of the causal mechanism. But Sir Ronald Fisher, who many of you would know, is an extremely eminent statistician, and that for many years said that smoking didn't cause cancer.
He also smoked.
Yes.
I think the others in the audience may...
And he was paid a lot by the tobacco industry.
But I think that there was a campaign to stop the medical GPs in the UK from smoking, and that made a big difference. That was all part, it's all the building up of evidence over, a body of evidence over a long length of time that eventually establishes what's actually
This
going
was the
on.
first study that showed that association. That's why it's a very famous case.
So Lynne,
Yeah.
Hill proposed 6 criteria for causation, and one of them was association through statistical analysis. And then there are many others. There's biological causability, temporal connection, something has to happen before something to cause it, and so on. And that's been embellished and expanded. And there's been an enormous number of literature on this topic of causation, which anyone who's serious about it should read, I think.
It's a whole research topic in itself. Yeah.
Absolutely.
Lynne, thank you very much for your talk. That was great. Can I just add a little bit on capture, recapture and its usefulness? one of Australia's more prominent statisticians of a few years ago did his PhD thesis on capture, recapture and variations on it, and I think thought that he'd be forever using it to estimate numbers of animals in the wild or things like that. And he was somewhat startled when one of his first usages of it was when the Victorian police came to him and said, "Can we estimate the number of prostitutes in St Kilda?" And of course arrest is capture.
Yeah.
And so it's a straightforward capture, recapture.
Well, you're a computer person. In the 1890 census in the US, it was the first census where they were recording the information on the computer. The whole of the computer was introduced. Prior to that, they'd sit there and count each piece of paper, okay? But then, of course, there were what we would call today recording errors. So they used this capture-recapture method to work out how many recording errors that they had or didn't have that was used there. So it's been around, it came from the 1800s, it's been around, it gets a lot of uses. But I do believe it was originally developed for a species, wasn't it?
Yeah.
Yeah.
You said something about statistical and mathematical thinking being really important for the future as we go on, evaluating the credibility of a claim and being able to kind of whether to take it in on yourself or to reject it. There's a lot of grey area where like the media and various kind of blurring the lines and using it for their own purposes, and I think generally, I don't know if you'd agree, but generally people have a pretty poor statistical understanding and approach to how they look at these kind of presentations of ideas. How do you see, what do we do, or what does society do to break through that? Because that is seems like quite an overwhelming force to for this application.
Yeah, I think it's a problem. Whenever I see the results of a study in the newspaper, okay, first thing I do is look to see the sample size. Was it 8 or was it 88 or what was it? Okay, if it's small, I don't even read the rest of it. I'm just not interested in it. But if it's a large study, then I may or may not, depending on the topic, be interested in it. I think we have to educate the journalists. Let them see what, statistical, like just the sample size issue, that's just one question. There are other questions, but whatever. The causation, that comes out all the time. Well, the spurious correlation, you see that constantly. It drives me crazy, because it's a misuse of statistics.
I think they're more interested in selling newspapers.
Yeah, they want headlines. That's for us, we want papers published. For them, I mean, not their papers, but that's their, that's their check-off points to get the promotions and things. And that's why some of it, I think, becomes worse than it should be.
It seems like, I guess, the incentive for journalists is to sell newspapers. So until they're incentivized to report things correctly, therefore, the population demands it, basically, of the product. That's not really going to happen, which basically requires more broad education of statistics, maybe younger schooling, even if it's really basic stuff, something like that to start that going. Because, yeah, as you kind of said, the journalists are just going to want to sell papers because that's the incentive.
Yeah. And if we read it and respond to it, then we're aiding and abetting it. We need to educate ourselves as well, or have our schools educate our families and our school children better. I mean, I think it's sort of interesting is that for me, wherever I've been in my life, mostly if there's something I know about, the newspaper article on it hasn't got it right. So why do I believe what the newspaper article says when I don't know anything about the subject? Aren't we all guilty of that? Yeah, if we're honest. So that's why I say I always scan through to see what, if they give me the, if they don't give me the sample size, I'm not interested in the result at all. But if they do, and so often it's, you know, really small samples. It's not worth the paper it's written on.
Sorry if that's okay.
Yeah.
Part of the problem might be as well that, especially now with so much media, so much saturation, and time pressure that people have, it might be difficult for people to check it. Ideally, you look at something, you analyze, okay, critically, okay, does this seem reasonable? Have they got sample size? Okay, maybe I'll do a bit more research. All of a sudden, that's already too much time.
Yeah.
So, yeah, it just seems difficult for the average person to really do that, I guess.
But the other side of that is that we want people to be able to use statistical thinking, mathematical thinking, so we do want these articles to be useful, correct? And so that's the bigger issue. How do we, as mathematicians, as statisticians, as educators, how do we get into that whole issue of that gets back to your STEM thing? How do we educate people?
If I could ask, in a month, we've got an election coming up.
Yeah.
We've got an election
Yeah.
coming up. A lot of statistics, and
Yes.
there will be a lot of things said. Do we, as mathematicians, statisticians, have an obligation to inform the public when there's something erroneous to its report? And we know it could be true. Is that an obligation? Because if it is, I think it's one that we're not following through.
I think we should. I wrote a letter to Congress and the presidents once,
That sounds like.
and I got a writer taken off the a bill.
Yeah.
Flood relief act. What? I think it's important to stand up.
Are there any other questions?
Yes.
Just one last question. Now New South Wales Ministry want to integrate the data from health, education, welfare, everything, and make policies that reflect the evidence. Do you think there's good scope for this?
Well, the symbolic data, the interval data example I had at the end, you know, because of the computer capacity, these data sets are going to be merged. We can't sort of say, no, don't do it, they're going to do it. Okay? And there's a lot of good information in those data sets that will answer a lot of questions that we have, but we just have to know how to analyze them. And so those ideas, I think, are not going to go away. I'm not going to say interval data, histogram data, what's called symbolic data is the only way to analyze large data sets, but I think it's a very important way. And that's why I added that at the end there, showed it to you. Yeah, it's going to happen, whether you like it or not.
So the methods haven't even been written for these problems?
No. I mean, that clustering using regression, I mean, that's not, we haven't written the paper yet. I mean, he only graduated last week. There's very little out there. Very little out there. There's a whole open world there. It's an exciting world. I'm just glad I've got 20 years left to keep working in it. But you guys have got 40 years and longer. Okay, there's a lot to be done out there. Yeah.
Well, I think we should thank Lynne again. I can't think of a person who is more worthy of being the first ambassador for the females in science and mathematics. So, thank you very much.
Well, thank you.
I want to thank you all for coming along. I want to thank the people who run the program, the Girls in Mathematics, that has been running here for 11 years. It is a very important initiative. We are committed to building up numbers of females in STEM. So thank you very much.